As you step inside a steel mill, the world transforms around you. Immense structures loom high, made of raw iron and steel, each one pulsating with life. In the heart of the mill stands a blast furnace, a behemoth of metal towering over the surroundings. This particular furnace, glowing with an orange hue against the dull backdrop of machinery, has not been turned off for decades. Its temperature has remained at a staggering 1500 degrees Celsius for a campaign lasting over 20 years. Here, in this unforgiving environment, the steel-making process continues unabated, unyielding to the passage of time. In a world where machines are expected to shut down for maintenance, this one defies convention, raising an inevitable question: why do steel mills never turn their furnaces off? The stakes of this inquiry extend far beyond mere curiosity. A blast furnace of this scale operates much like a colossal kettle, turning iron ore and other raw materials into molten metal through an intricate dance of chemistry and physics. Yet, while most machinery can, theoretically, be halted and restarted, the sheer size and complexity of a blast furnace render such an operation a perilous endeavor. So why do these giants rarely cool down? By the end of this exploration, you will understand the underlying mechanism that keeps these impressive structures running continuously. To grasp why steel mills maintain the heat of their furnaces, we must first look at the furnace's internal workings. Inside the blast furnace, a delicate yet powerful chemical reaction takes place. Iron oxide, in the form of ore, is fed into this towering structure along with a mixture of coke, essentially carbon, and a flux material such as limestone. At the furnace's peak, raw materials descend while a superheated blast of air, reaching approximately 1000 degrees Celsius, is introduced from the bottom. This combination generates extreme heat and drives the chemical reactions necessary to reduce the iron oxide, allowing molten iron to accumulate in the hearth. The heart of the furnace, the hearth, is subjected to excruciating temperatures, typically ranging between 1500 and 1600 degrees Celsius. At these levels, any exposure to air when the furnace is turned off would lead to oxidation. The coal and preheated air would also need perfect conditions to sustain combustion, made increasingly difficult once the heat dissipates. As temperatures fall, the risk of thermal shock becomes the prime concern. This brings us to our first critical point: thermal shock. When the materials within a blast furnace cool, the refractory lining, that is, the firebrick that protects the furnace walls, can crack and weaken. Engineers estimate that if a furnace were turned off and allowed to cool, the subsequent reheating could lead to a dangerous compromise of structural integrity. Switching it back on would require both time and energy, a fact magnified by the sheer volume of material that needs reheating. Once cooled, the furnace would take days, if not weeks, to reach operational temperatures again, making the logistics of a restart exceedingly inefficient. To appreciate this, consider the case of the U.S. Steel Corporation's Edgar Thomson Works in Pennsylvania. When engineers evaluated the costs of restarting furnaces after scheduled maintenance, they found it significantly cheaper to run 24/7. They also recognized that keeping the furnace at peak operating temperatures minimizes the risk of catastrophic failure from thermal shock, a risk deemed unacceptable in an environment where molten metal swells and contracts. This brings us to a second layer of complexity: what happens inside the hearth when the temperature wanes. If the furnace is allowed to cool significantly, a frozen hearth situation can arise. As the molten metal solidifies under cooling conditions, iron and slag may harden, creating a blockade that could entirely halt operations. Removing this blockage to restart production can involve significant manual labor and expensive downtimes, effectively countering any perceived benefits gained from a cold shutdown. If we were to visualize this, imagine a situation in which a massive transportation vehicle, like the cargo ship Emma Maersk, a container ship measuring roughly 400 meters in length, stopped in the middle of the ocean simply because it needed to cool its engines. Such a vessel operates at a scale and complexity where stopping would mean years of delays and millions of dollars lost. In the same vein, a blast furnace treats its thermal maintenance as a non-negotiable necessity for operational efficiency. Now, let us pause for a moment and turn our focus inward. Which of these machines would you least want to be standing next to, a cold, dormant blast furnace with the weight of molten metal above, or a vessel navigating turbulent waters? Take a moment to share your thoughts below. One might be tempted to reason that simply turning off a furnace during downtimes would save energy, cut costs, and be a sensible approach. But here, another misconception emerges. Many assume that reducing power consumption is the ultimate goal of engineering efficiency. In reality, for blast furnaces, the engineers do the exact opposite. They find value not in turning off the furnace but rather in ensuring it never cools down. This approach is not merely about cost but revolves around an essential truth of industrial operation: continuous production equals sustained economic viability. Stopping the furnace sacrifices efficiency for the sake of temporary energy savings, whereas maintaining relentless operation delivers molten steel consistently, ready for fabrication and shipment. Thus, the true trick lies not in a simple on-off switch but in an understanding of culinary heat, the process of keeping the forge hot to prevent costly interruptions and material waste. Moreover, considerations of safety further reinforce the decision to keep furnaces running at incredibly high temperatures. Engineers are acutely aware that any fluctuation in temperature can lead to unexpected failures, creating an impetus to maintain consistency. A study by the American Iron and Steel Institute notes that the U.S. steel industry alone produces over 90 million metric tons of steel annually, making the continuous operation of blast furnaces not just a goal but a critical operational strategy. As we reflect upon these revelations, we come to realize that the invisible engineering behind such colossal machines informs much of our daily existence. Within these massive structures, the precision of thermal dynamics governs not only the temperature of molten metal but the very productivity of entire economies. To see a blast furnace as merely a large assembly of bricks and metal would be to overlook the intricate ballet of chemical reactions and heat management that breathes life into it. In closing, we are surrounded by impossible machines that somehow just work. Each blast furnace, whether operating continuously for decades or composing the heart of a sprawling steel mill, serves as a reminder of human ingenuity and our ability to harness complexity into something efficient, productive, and remarkable. You have witnessed the trick. Keeping the furnace hot is not merely about manufacturing steel, it is about ensuring that the modern world, and indeed, our economy, continues its relentless forward momentum. Now, as you step away from this exploration of the blast furnace, consider the giant mechanisms that shape our lives. Subscribe, one giant decoded at a time. Continuing our examination of blast furnaces, we delve deeper into the unseen complexities that govern their operation. One critical factor is the energy requirements and fuel efficiency. A blast furnace is an energy-intensive entity, and yet its engineering allows for a remarkable use of waste heat. As it operates continuously, the furnace generates significant waste heat that can be reused, thus enhancing the overall energy efficiency of the steelmaking process. For instance, modern blast furnaces are often equipped with heat recovery systems that capture this waste heat and utilize it in various stages of production. These systems can recapture heat from the flue gases and use it to preheat the incoming air used in the combustion process. By recovering heat that would otherwise be lost, steel mills can improve their thermal efficiency by as much as 30%. This is a crucial statistic, especially considering that each ton of steel produced can require up to 500 kilograms of coke, which must be burned at high temperatures. By maximizing the heat from the process, mills reduce their dependency on additional fuel and lower operational costs. An example of this efficiency can be seen in the ArcelorMittal plant located in Ghent, Belgium. This facility showcases how integrated heat recovery systems not only cut down energy consumption but also minimize greenhouse gas emissions. By implementing advanced heating strategies and efficient energy usage, the plant achieves a carbon footprint significantly lower than older, less efficient mills. Equally fascinating is the environment within the blast furnace itself. A furnace operates on a delicate balance, blending chemistry with physics to facilitate the iron reduction process. This journey begins when iron ore enters the furnace from the top, accompanied by coke and limestone. As these materials descend, a carefully controlled airflow is introduced. The air is heated and enriched with oxygen to facilitate combustion. This process is crucial because it creates an internal environment of extreme temperatures and pressures, sometimes exceeding 2.5 atmospheres at the hearth. The choice of coke as a fuel and reducing agent is essential to this process. Coke, produced through the destructive distillation of coal, is not only an energy source, it also provides the necessary carbon for the reduction reaction. When combined with iron oxide in the intense heat of the furnace, carbon dioxide is expelled, and pure molten iron is left behind. Notably, the chemistry involved is represented by the reaction, Fe2O3 plus 3C2 Fe plus 3CO2. This interaction highlights just how intricately biological materials, geological elements, and thermal dynamics intertwine to produce steel, the backbone of modern civilization. Compounding the complexity is the behavior of molten iron in the hearth. As the temperature exceeds 1,500 degrees Celsius, the iron maintains a liquid state, flowing toward the tapping point at the base of the furnace. However, a deeper understanding of this molten metal behavior reveals a crucial element, viscosity. At the extreme temperatures present in the hearth, molten iron exhibits relatively low viscosity, which does not impede its movement to the tapping point. But if the furnace were to cool, even slightly, that viscosity would increase, posing risks of solidifying, thus forming clogs and blockages. This phenomenon is a constant reminder of the precision required in managing a blast furnace's thermal environment. Additionally, the role of operational continuity is underscored by maintenance considerations. The complexity of the blast furnace demands a proficient workforce trained not only in the operational procedures but also versed in troubleshooting the sophisticated array of monitoring systems in place. Modern furnaces are equipped with sensors and controls that track temperature, pressure, and chemical levels continuously. This level of monitoring allows operators to react promptly to any fluctuations that could compromise the process, ensuring they can maintain optimal conditions among the scorching chaos. Historical context provides insight into the evolution of blast furnace technology. Early furnaces, such as those used during the Industrial Revolution, were able to produce cast iron using much more rudimentary techniques. Today's process reflects over 2 centuries of innovations in metallurgy and materials science. For example, the first known use of a blast furnace in England is credited to the Wealden iron industry in the early 16th century, which operated on a much smaller scale and was susceptible to the inconsistencies of low-quality ore and limited fuel sources. Advances in technology have allowed us to refine the materials employed and enhance chemical knowledge, allowing for massive facilities that produce thousands of tons of steel daily. Let us consider an anecdote that reflects on the critical importance of understanding each unique component within this giant machine. In 2010, a blast furnace in an integrated steel mill experienced an unexpected cooling event due to a cyclical failure in its air supply system. As temperatures began to plummet, pressure within the hearth increased, leading to blockages and ultimately a prolonged shutdown that took over 2 weeks to rectify. The estimated losses were not only financial, totaling nearly $1 million, but also included the potential structural failure of the furnace, a risk that engineers had to mitigate at every turn. This event serves as a testament to the fact that within the world of gigantic machines, a singular failure in the system can have cascading repercussions. In bridging the science with the art of engineering, we discover the fundamental truth governing blast furnaces: they are not merely furnaces, they are continuous, living systems characterized by feedback loops and homeostasis, designed to function in harmony. So, while these structures appear as monotonous behemoths of copper and steel, they are anything but simple machines. They are a complex amalgamation of processes tied to human ingenuity, reflecting the collective advancement of our technology. Moreover, the importance of maintenance implications should not be understated. Routine inspections and careful monitoring allow engineers to identify early signs of wear or damage that could lead to substantial operational risks. In fact, projects aiming to improve the longevity of furnace linings have evolved to include advanced materials, capable of tolerating higher temperatures and even improving the non-stick properties of the inner hearths. For example, new ceramic fiber linings are being tested for their ability to withstand the extreme thermal environment, allowing for longer campaigns and minimizing downtime. The means of cooling a furnace if it needs to be shut down should it require repairs are equally complex, each engineered solution springs from the need to mitigate the risks associated with cooling. If ever a blast furnace must cool, the preferred method is controlled cooling, a process that introduces cooling materials strategically while the furnace is kept under controlled conditions. This method extends the operational life of the structure and provides safety assurance to the workers involved. As we appreciate the vast network of systems supporting a continuous steelmaking operation, we also recognize its broader implications on global commerce and economy. Steel produced in blast furnaces is essential in constructing bridges, buildings, vehicles, and a multitude of products we engage with daily. Steel accounts for nearly 1.7 billion metric tons of production globally, making it a fundamental bedrock for countless industries. The continuous operation of these furnaces, thus, has economic ramifications that reverberate far beyond the walls of the steel mill. In this light, we must reflect upon the future of blast furnaces within the context of sustainability. With pressing demands for cleaner production methods, the steel industry faces challenges to reduce carbon emissions significantly. Innovations such as electric arc furnaces, which recycle scrap steel and utilize electricity rather than fossil fuels, are gaining traction as alternatives to traditional blast furnaces. However, they currently face limitations in scale and initial production costs. This motivates ongoing research and dialogue about how to integrate the established systems with emerging technologies in a landscape that values both efficiency and environmental responsibility. Thus, the reasons behind a blast furnace's indefinite operation emerge not merely from practical considerations of efficiency or mechanical integrity, they are enmeshed within a tapestry of economic, environmental, and operational paradigms that shape our modern lives. The mastery over temperature, pressure, and time transforms raw materials into the lifeblood of industries. To encapsulate this journey through blast furnace principles, we acknowledge that their relentless operation serves a dual purpose of producing vital steel, as well as affirming the underlying engineering philosophies that keep it functioning. As we stand in awe of these magnificent structures, it is essential to remember that our modern world is a product of continued innovation and relentless optimization found within these massive machines, crafted by generations of engineers dedicating their expertise to a constantly evolving discipline. In closing, let us appreciate that we are surrounded by impossible machines that somehow just work. The journey of a blast furnace, its heat, its adversity, and its silent, powerful efficiency, mirrors our pursuit of innovation and progress. Remember the trick: keeping a blast furnace hot not only generates steel but ignites the engine of an economy that relies on its unwavering continuity. Subscribe, one giant decoded at a time.